Hello everyone. Today we'll be discussing the third module of CN super important questions. So in this module there are 5 questions which have been taken from the model paper as well as in the previous scheme papers, which are the most repeated ones. Make sure you watch this video till the end. Easily you can score more than 80% marks. And before starting, please do like and subscribe. It helps me make more videos like this. So without wasting any more time, let's get started. The first question is explain a Dijkstra's algorithm and show how to form least cost tree with an example. Okay. Also, the same question can be asked in a different way. Explain the link state algorithm. Okay, link state algorithm is also same as the Dijkstra's algorithm. So if both of these question comes, you have to write the same algorithm. Okay, and another thing they have asked is how to form the least cost tree with an example. That also will be discussing. Okay, so Dijkstra's algorithm is used to find the shortest path between the nodes. Okay, between two nodes, what is the shortest path? That is found by the Dijkstra's algorithm. Okay, so the algorithm is given below. You have to start it like this. Dijkstra's algorithm. Okay, there is an initialization part and calculation part. Okay, two parts is there. The first is the initialization part and second is the calculation part. Okay, so let's understand what is the initialization part. So in we have to form a least cost tree. Okay, so since we need to form a tree, we'll be taking the root node into the tree initially. Okay, tree is made of only the root. Okay, then we will run a for loop. What we will run? We will run a for loop from 1 to n. N is the number of nodes. Okay, if y is the root, okay, in case if y is the root, then distance to y will be 0, because from root to itself the distance will always be 0. Okay, else if y is a neighbor, that the cost of that means from moving from y to its neighbor, what is the cost, that will be stored in d of y. Okay, so that will be defined in cost of root to y. Okay, c is the cost array which will be having the cost from root to y. Okay, that will be stored in dy. Else if it's not a neighbor also, then it means that it is not reachable. Okay, that node is not reachable, because it's not always that all the nodes are connected to each other, right? Some nodes will be there which will be connected to other nodes, but this and this node is not connected here, right? So that in that case the cost will become infinity there. Okay, so this is the initialization part. First is the tree is equal to root and second is one for loop. Okay, with if and else condition. Next is the calculation part. Here we will be repeating it. Okay, repeating means it will be do while loop or a while loop. Okay, so what is the condition? Until all the nodes are included in the tree. So the tree which we had defined above, the tree array, that should be having all the nodes. Okay, all nodes should be there, then only we'll be stopping. Until all the nodes are not there, we will not stop. Okay, so the first thing is find a node w. Okay, we have to find a node w such that with d of w, means distance of w is minimum among all the tree nodes not in the tree. Okay, so see, in the tree some nodes are there. Okay, there are two scenarios. In the tree some nodes are already there, and the ones which are not there, those are present here. Okay, so among this, which is having the minimum cost, that we will be taking, and that node will become w, and that we will have to add it to the tree by taking a union operation. Okay, now the tree will be having a new node. Okay, for that new node we will be running a for loop where every node x which is a neighbor of w not in the tree. Okay, it is a neighbor of w but it is not in the tree, means w might be connected with some other nodes, right? So we'll be taking each of those node into consideration in the for loop. Okay, and what we will be doing, we'll be writing d of x, means till that neighbor x. Okay, w is here and we have taken w, and suppose that this is the root node y. Okay, from y to x we'll be finding the distance. Minimum of d of x means direct distance. Okay, this is y, this is x, direct distance is more, or dw plus cwx, or y to w and w to x. Okay, this is more, means which is less we will be calculating. If I go through w, that will be less, or if I go directly, that will be less. Okay, based on that I'll be taking the answer here. We'll do that for all the nodes. Okay, so that at the end of Dijkstra's algorithm we'll be having a tree set which will be having all the nodes with the minimum path. Okay, so the same thing is described here also. You can go through the theory part here, but whatever I have explained about that also, if you write in your own words, that will also be sufficient. Okay, now to create the least cost tree, each node needs to run lsdb algorithm. What is lsdb? Link state database algorithm. Okay, that is same as the previous one, Dijkstra's algorithm only. Okay, so let's consider an example here. Okay, so the following graph is given. Since they had asked the example, this is the example here: a, b, c, d, e, f and g. So 7 nodes are here, and the cost is also given here. From the a to d the cost is 3, a to b the cost is 2, b to e the cost is 4, and so on. Okay, so these are the nodes here, and this is the table. So from a to a the cost will be 0, from b to b the cost will be 0, from c to c the cost will be 0, from d to D, the cost will be 0. So the middle diagonal will always be 0. Okay, and the other ones, A to D and D to A, both will be 3. Okay, so see, A to D, it will be 3, and D to A, that will also be 3. Okay, so in that way you'll be filling, and whichever is not connected, see, A and C is not connected, it is connected via B, but directly it's not connected, right? So A and C, that will be infinity. Like that we'll be filling this table here. Okay, so after filling the table we have to find the least cost, means which path is the least. If suppose what I mean is, I want to go from A to E. Okay, I want to go from A to E. If I go through B, my cost will be 2 plus 4. If I go through D, my cost will be 3 plus 5, which is more less, which is lesser. This is 8, this is 6. So this is my least path to go to E. Like that we'll be calculating for all the nodes. Okay, so least cost tree formation is same by using that algorithm. We'll be starting from A. Okay, now from A I have two options. I can go to B, I can go to D. Which is more easier? To go to B, I have the cost is 2. To go to D, the cost is 3. Which is more, which is lesser? The 2 is lesser, right? So that's why I will be taking this as a solid line, and this will be still a dotted line. Okay. Next, from B again, I'll have an option to go here or here. From B, if we have a look, 5 and 4, which is lesser? Obviously, 4 is lesser, so I'll be going to E. Okay. So see, I have gone to E. Now from E to F, that is only single path. So if I go from E to F, that will be cheaper, or if I go from B to C, that will be cheaper. Okay, so let's have a look. If I go from E to F, my cost is 2. If I go from B to C, my cost is 5. Okay, but to go from E to F, I had to cross this also, right? 4 plus 2, that is lesser, or 5 is lesser? Obviously 5 is lesser, but since we have taken this path, you have to take this one also. Okay, got my point? I'll repeat. See, we have taken this path. Okay, now the question is whether this path is smaller or this path is smaller. If we take it separately, this path is 5, this path is 2, this will be smaller, but to reach here I had to go through here, so I have to take this also into consideration. So 4 plus 2, it will become 6. Okay, and this will be a direct path, which is 5. Now in this case, this is smaller, I can take this one. Okay, I can take this one, but I also had taken this path already, right? I had taken this path already, so I'll be taking this one also. Okay, afterwards we'll consider which one to consider. Okay, but for now we'll be taking this one as and this one as well. Okay, so both of them will be taken into consideration. Okay, see, here we have taken both of them. Okay, now like that we'll keep on continuing. E to F, then we'll be considering, and from F to G. Okay, so from C to G we don't have, so that's why we have to take this one, E to F also. Okay, to reach C, my only path is B to C, that's why we have taken this path. Okay, we cannot ignore this path, otherwise C will be unreachable. Okay, E to F and F to G. Okay, got the point. Based on that, we have to analyze and solve the problem. Okay, so either they can give you a graph in exam, or they can ask you to give an example. So you can take this example, just practice it 3 times, 2 to 3 times, you'll be able to keep it in mind. Okay, so that was about the first question, Dijkstra's algorithm or link state routing algorithm. Okay, both are same. Moving on to the second question, which is OSPF and BGP protocol with an example. Okay, so OSPF means open shortest path first, BGP means border gateway protocol. Okay, let's understand each one by one. OSPF is open shortest path first. Okay, OSPF is an intra-domain protocol. Intra-domain means what? Inter-domain means between domain 1, domain 2, domain 3. This is inter-domain. Okay, between the domains. Intra-domain means inside one domain the connections are made between the different parts. Okay, that is called as intra-domain. So OSPF is what? It is intra-domain protocol. It is based on link state routing protocol. Okay, it is based on link state routing protocol. And OSPF, each link is assigned a weight. Okay, so each link will be having a weight like the cost. Okay, how much it is to cost from going to this here to here. That cost will be depending on throughput, round time, reliability, and so on. These factors calculate what will be the weight of that link. Okay, the following diagram illustrates the cost. For example, here I have N1, N2, N3, and N4. Now, from N1 to N4, if I go directly, my cost will be 12. Okay, the cost will be 12. If I go through R2, the cost will be 7. If I go through R3, it will be 4. Okay, so the costs are given here. This is 4, this is 5, this is 3. So if I go directly like this, it will become 4 plus 5 plus 3 plus 4. Okay, if in case if I go from here, the cost will be 5 plus 3 plus 4. If I go from here, the cost will be just 4. Okay, so you get the point, right? This is 4, this is 3. 4 plus 3 is 7, so it will be 7 here. 4 plus 3 plus 5, it is 12, so it will be 12 here. Okay, initial cost will not be considering. Okay, so each OSPF can create forwarding table after finding all the shortest path tree between itself and the destination using Dijkstra's algorithm. Okay, so here we'll be having the Dijkstra's algorithm. This is the link state routing algorithm. It uses Dijkstra's algorithm only. So after finding all the shortest paths, see the shortest paths are given here. The shortest path after finding we'll be putting it into a table. Okay, as you can see the forwarding table for R1. R1 is the router one. R1 and can directly travel and reach the destination, so the cost is 12. So n1, the means the next router, there is no next router for n1. N2 also there is no next router. For n3 there is R2 which is 8 cost, n4 it is R2 which is 12 cost. So from n3 and n4 it's connected with R2. Okay, n3 and n4, which is n3 is this one and n4 is this one. Okay, so R1, it is connected with R2 for n3 and 3 for n4. Okay, like that. And the cost is also taken. The first one is the 8 and second one is the 12. Okay, so you need not actually make this as means given here the exact values and all. You get the point, right? So we are traveling from one point to another point using a router, and some costs are associated with that based on the diagram. Okay, just have to explain it theoretically. The values they will not be checking it. Okay, so you can write any values here, just explain the theoretical concept very well. Okay, now there are areas in autonomous system. Okay, what do you mean by area? This is area 1. Okay, this is area 2. Okay, this whole thing is the area 2. This is the area 0. Okay, area 0 is a backbone area. Okay, and this whole thing is called as autonomous system. Okay, now see, this group is called area 1, this group is called area 2. To connect these two areas there is a backbone area. Okay, backbone area will be connecting all the other areas. Okay, and this whole thing will be connecting another AS, which is the autonomous system. This whole thing is one autonomous system. There will be another autonomous system that will be connected by the AS boundary router. Okay, so internally connections are there, area border router, and the external connections will be AS boundary router, which is the autonomous system boundary router. Okay, so this is how OSPF is designed. Okay, in OSPF you will be having different areas with different protocols inside them. So OSPF is implemented as a program in the network layer using the services for the IP propagation. OSPF messages are encapsulated inside the datagram. Okay, if the messages are being transferred, the message 1 is being transferred, they will be encapsulated into a datagram. Okay, it will be in the form of datagram. Okay, and OSPF algorithm slightly differs from the link state routing algorithm because there are autonomous system involved, and area borders, area routing, there is a backbone here, and the different routers are present in inside them as well. So because of these things there will be slight changes from the link state routing algorithm. Okay, so but it is implemented on the link state routing or the Dijkstra's algorithm only. Okay, so these are the things you need to write for the OSPF. Moving on to the second one, which is BGP, which is Border Gateway Protocol version 4. Okay, so usually we'll be using version 4 only. So Border Gateway Protocol version 4 is the only internet inter-domain routing protocol used in the internet today. So current internet today, it works on which protocol? Border Gateway Protocol. Okay, repeat with me. The current internet protocol which is there all over the world, it works on BGP, which is Border Gateway Protocol version 4. Okay, so it is inter-domain protocol. Inter-domain means domain 1, domain 2, domain 3. And how these domains are connected? These domains are connected by BGP, which is Border Gateway Protocol. Now it is based on path vector algorithm or the Bellman-Ford algorithm. We'll be discussing the Bellman-Ford algorithm in the next question. Okay, it is based on Bellman-Ford algorithm. The following diagram shows an example of internet with 4 autonomous systems. Okay, so there is a 4 autonomous systems here. Like previously I showed you what is inside an autonomous system. Like that, this is one autonomous system, this is another autonomous system, another autonomous system, another autonomous system. There are 4 autonomous systems: AS2, AS3, AS4. Okay, AS2, AS3 and AS4. These are what? These are the sub autonomous systems. Okay, and A1 is the transient one, because if you observe carefully, this is a smaller one and this is a smaller one, this is a smaller one, and all of them are connected to this one, which is a major one. Okay, and the line also you can see, this is a thin line here. Okay, so this is an inside one autonomous system connection. This is also inside autonomous system connection, but here you can see there is a point to point link. Okay, This is a point-to-point wide area network. So this is a major like a backbone. Okay, in the previous one we had seen a backbone, right? So this is the backbone for BGP. Okay, so a sample internet with 4 layers. You just have to make it like this, very simple. Just make a cuboid here and here and connect it with a circle called as the router. Do it for the same for the other two as well, and connect it with another one, and mark this as the transient one and the other one as sub autonomous systems. Okay, each autonomous system above uses either routing information protocol or open shortest path first. So each of these inside, okay, these use any of the algorithms like OSPF and routing information protocol. To enable each router to route a packet at any network in the internet, we use external BGP. Okay, so we use two types of BGP. External BGP will be connecting these two. Okay, external BGP, external BGP, external BGP. These are the external BGP. Okay, internal BGP will be making a connection in between them. Okay, that's the difference. To enable, we install the external BGP for enabling the route to route a packet to any network in the internet. If I suppose that R5 wants to send some message to R9, we will be implementing eBGP so that it sends first here, then iBGP will send from here, and eBGP will be sending from here. Okay, so that is eBGP. The other one is internal BGP, iBGP, on all routers to transfer the information within themselves. Okay, eBGP allows two physically connected border routers to in two different ASs to form a pair and exchange the messages in two different ASs. Right, that's the main point here in eBGP. This is one AS, this is another AS. If you want a connection between them, eBGP here, eBGP here. If you want to send the messages internally inside the same autonomous system, we'll be using a iBGP. It creates a session between the routers in the same autonomous system. Okay, that was about the BGP. Let's move on to the third super important question, which is explain Bellman-Ford algorithm with an example. Also, if they ask you about the distance vector algorithm, that is also same only. Okay, distance vector or path vector, all of them are same. It comes under the same topic, Bellman-Ford algorithm. So, what is Bellman-Ford equation? It is used to find the least cost. Okay, it is used to find what? Least cost means shortest distance between a source node X and a destination node Y. This is the starting point, this is the ending point. From X to Y I have many paths. Okay, which is the shortest path among these? That is found by the Bellman-Ford algorithm. Okay, through some intermediary nodes ABC, means in between also nodes will come through which we'll be connecting, and we'll be finding which connection makes the least cost, and that will be taken into consideration. Bellman-Ford equation uses the following to calculate the cost between node X and node Y. Okay, so between X and Y the cost will be calculated by using this equation. So we'll be having minimum. Direct path is smaller, or if you pass through Z, it will be smaller. CXZ means what? The cost from X to Z, that, and then from Z to Y, this is smaller, or if I go directly from X to Y, this is smaller. That minimum value will be taken and put into here. So from X to Y, the minimum path will be stored here and the minimum cost. Okay. So the following diagram shows the implementation. Suppose I want to go from X to Y. So as you can see here, there is three paths: through A, through B, and through C. So the cost through A, cost through B, cost through C, plus A to Y the cost, B to Y cost, and C to Y cost. Whichever addition is smaller, this one or this one or this one, that one will be taken into consideration. And whenever it is taken, we will be updating it as a straight path. Okay, suppose that if this is taken into consideration, we will be updating it as dxy, which is the path, and the total cost will be equivalent to this plus this. Okay, we use distance vector to keep track of the costs. Okay, like the previous one we used the forwarding table, right? So here we'll be using distance vector, okay, to keep the track. An example of distance vector is given here. From A to D the cost is see, from A to A the cost is 0, from A to D the cost is 3, A to B the cost is 2. So like that we'll keep on writing. See, from A to B the cost is 2. Okay, and A to D the cost is 3, so A to D the cost is 3. A to C the cost is written here 7, so A to C the cost is 7. So based on this tree graph, we will be writing it into a table that is called as the distance vector table. Okay, and the algorithm is as follows. Let's go through it quickly. So here we have two parts are here. Okay, actually three parts are there, but this can be taken into a single part. Okay, so see here what's happening. Distance vector routing. Here we will be calculating means initializing one array D, and it will be having initially 0 nodes. Okay, and then we'll be running a for loop from 1 to n is the number of nodes. If y is a neighbor, we'll do something. If y is not a neighbor, we'll do something. If y is a neighbor, we'll calculate the cost from the root to the y, and that will be stored here. If y is not a neighbor, the cost will be infinity, and after calculating all the d values, we'll be sending it to all the neighbors. Okay, and then if we'll be updating it. Updating means what? If any shorter path we find, so we'll be waiting for a dw neighbor from any change in the link. From y to n again we'll be running the same thing and checking if the new path of dy which we have got, that is smaller than if we go through another node w. In case w has come, okay, see, I have the direct path. Okay, now if another new path comes like this, I have to check that, right? And this is a w, so I'll be checking the cost to w from myself and plus the cost from myself to y, that is smaller, or direct path to y is smaller, and that will be updated here. Now, after that, if any changes in the vector, whatever, if any changes happened here, that change will be updated and sent to all neighbors, so that neighbors will be having the updated values. Okay, very simple. First part is the initialization part of the direct paths, and this will be in case any middle node comes as w, we'll be checking if we'll be testing if any w is there such that it is having a lesser cost. We'll be calculating it here and we'll be updating it and sending it to all the other neighbors. Okay. Moving on to the fourth super important question, draw IPv6 datagram format and explain the fields. Very, very important question. Don't miss this at any cost. Okay. So here IPv6 datagram format. Okay. The first thing you need to draw is this one. Okay. The packet. In the packet, we will be having the first 40 bytes for the base header, and the rest of the thing will be having the payload. This will be having the actual data, and base header will be having some metadata. Okay. What will be the metadata? This is the metadata. Okay. This is the base header. So you can imagine it like this. This is the expansion of this. Okay, this is the expansion of this. So we have to write this and define each term. Very simple to remember. Destination address, source address. Half of the diagram is done. After that, you'll be starting from here. This is the first thing, is the version. What do you mean by version? Version means it will be defining if it is IP6 or IPv4. Okay, that is the version. Second thing we have is the traffic class. Traffic class means it is an 8-bit which is used to distinguish between different payloads with different delivery requirements. Means there will be different types of data and different lengths of data, which class that data belongs to. First is the version, second is the traffic class, third is the flow label. What do you mean a flow label? It is a 20-bit field that is assigned to provide a special handling for particular flow of data. Okay, so it will handle the particular flow of data, that is called the is the flow label. Payload length means what is the length of the data, means whatever the data which we have here, what is its length. Okay, that length will be stored in the payload length. Okay, after that we have the next header. Next header means after this header, which is the next header I have to go to. Okay, the next header is an 8-bit field that defines the type of the first extension header or the type of data that follows the base header in a datagram. Means there will be many headers, so this header will be having what is the information of the next header, next will be having where it is the next header, and so on. So that next header information will be there. After that is the hop limit. Hop limit means how many times it can pass through until it stops. Okay, pass through different layers until it can stop. Okay, that is the hop limit. Okay, there is a limit defined. After that, it's very easy. Source and destination address, 128-bit address of the datagram, and payload is the actual data that is to be transmitted along with some other information. Okay, this very simple question, but very, very important from the exam point of view. Don't miss this question at any cost. Okay. Moving on, we have the last super important question, which is explain DHCP and its importance. Okay, very interesting question. DHCP is Dynamic Host Configuration Protocol. Okay, what it is? Dynamic Host Configuration Protocol. Okay, it is a protocol that configures the host dynamically, means based on requirement. Okay, host is a server, so it configures the server or the main system based on the requirement. Okay, it is an application layer protocol. Okay, it is which layer? Application layer protocol that helps the transport layer, IP, TCP IP at the network layer. Okay, so it's interconnected with different layers. DHCP has found widespread use. Okay, means there is a lot of use of DHCP in the internet, and it is called as plug and play protocol. Okay, now what is its importance? A network manager can configure DHCP to assign permanent IP address to host and the routers. Okay, first is to assign permanent IP address to the host and the routers. For that, DHCP will be used. DHCP can be configured to provide temporary IP addresses. In case the addresses are not available, a temporary address can be assigned based on the requirement. That also DHCP will be doing. DHCP can be used to provide important pieces of information to the host. Okay, for the host, there will be some information pieces required. That information can be fetched via DHCP and that will be provided. Okay, the following diagram shows the message format. Okay, you need not remember this diagram, just take a glance of it. Okay, try to remember as much as possible. That's totally fine. So here we have the operation code. Here h type, h length, and h count. What is h? H is nothing but hardware. Okay, hardware type, hardware length, and hardware count. And after that we have the time here, and we have some flags here, and here's the IP address for the client and the server, and here we have the server name. boot file name and the options. You can go through this part and try to remember as much as you can, but make this diagram THCP message format and include whatever you can. Okay, at least you'll get some marks. Okay, but don't spend more time trying to memorize this one. Okay, an example situation where the DHCP is being used. Okay, if you want, you can make this in diagram. Means in exam you can make this one. In case you are not able to write more information about this one, because this is comparatively easier to remember. So here, what's happening? How does DHCP work? Okay, DHCP discover will happen first. It will have this information. Means where it is starting from. That information will be there from the client, and that will be sent to the server. Okay, and from the server the DHCP offer will happen. Okay, means some task is to be performed, that will be the task will be offered to the client. Okay, so the client will be here and the tasks offer will be accepted here, and the request will be sent to the server, continue the execution or whatever the task is. The next step is that which is to be performed, that will be sent on DHCP request. After the request has been successfully received here, that will be sent back as DHCP acknowledgement. Means it will inform the client that the DHCP request was successfully accepted here. Okay, like that it will keep on going. There are few more things, the options for DHCP are there, but for an simple example this much is enough. Okay, you got the point, right? What is DHCP? It helps to configure dynamically the host. Okay, that's all for this video, and please do like and subscribe. It helps me make more videos like this, and thank you so much for watching. I'll see you in the next one.